Hello everybody. Welcome back to Thermo. Today we're going to be doing a turbine example problem, okay? Now we've learned a little bit about turbines and how they work, and now it's time to actually apply that knowledge to an example problem. So here, I have a problem. You will also see it in the description probably. An adiabatic gas turbine expands air at 1300 kilopascals and 527 degrees Celsius to 100 kilopascals and 127 degrees Celsius. Air steadily enters the turbine through a 0.2 meter squared opening with an average velocity of 40 meters per second and exhausts through a 1 meter squared opening. Determine A, the mass flow rate of air through the turbine, and B, the power produced by the turbine, right? Now, remember I said that there are a few things that we're going to want to do in these problems for us to get full credit. First, we're going to want to identify the system. So the system is probably the easiest part to identify. You can say, they told us it's a turbine containing air, right? So that's literally our system. An adiabatic turbine, I'm just going to write it here just to give us space since we're using a little bit of a small board. Adiabatic turbine with air. Boom, easy. Adiabatic turbine containing air, adiabatic turbine with air inside of it, blah, blah, blah. It just covers the same thing, right? Next, what you can do, maybe you want to do your sketches, right? Now, a sketch will sort of look something like this. Let me see if I can use this. Sketches, right? Now, with our sketches, we're going to want to include a state diagram. Sometimes I might just know what the state diagram looks like. Sometimes I might come back to it. In this case, I'm probably going to come back to it. But this is what our sketch is going to look like. Alright, something like this. So we're going to have our P2, T2, H2, right? P1, T1, H1. And it's going like that, right? Then we're also going to have work out because it's a turbine, right? Work dot, power. And then what you can also do is just draw like this to just imply that that's our system that we're looking at, right? Since we're dealing with an open system, we can just look at that. Right, it's sort of, we're looking at that. You don't really have to do that. They should still give you credit. But basically those dashed lines just imply that, oh, that's my system right there. Now, okay, what I like to do, right, as you've seen, I'm going to go ahead and use red. I like to write out all of the properties that they've given me. So I know that it's expanding air, right, from 1300 kilopascals and 527 degrees Celsius, right? So my P1 is 1300 kPa. My T1 is 527 degrees Celsius, but what do we have to do? Because we're dealing with an ideal gas, we have to convert that to Kelvin, right? Now, I'm going to go ahead and convert that to Kelvin by adding 273 degrees, and that gives me 800 Kelvin. So I'm just going to write equals 800 Kelvin. You know what I'm going to go ahead and do? I'm going to go ahead and erase this because I don't have too much space, so I can sort of write this a little bit to this side, and I can go ahead and, you know what, let's see if we have space actually. Alright, and then we know also our P2 and T2, right? P2, it said, was 100 kilopascals, and T2 is 127 degrees Celsius, which should be 400 Kelvin. And it sort of makes sense, right? We know that with turbines, our pressure is going to go down, right? Because we're producing work at the expense of pressure, right? So that makes sense. We can sort of use that to just check ourselves, make sure we're on the right track. So they're asking, okay, average velocity also. So you can write like, well, no, don't worry about that. Not V1. Actually, it is V1. I apologize. But we'll come back to that. So what we're going to do, we're looking for the mass flow rate, right? We know that, okay, first of all, what I want us to do is solve for V1. And how are we going to solve for V1? Our V1, since air is an ideal gas, right, we can go ahead and use the ideal gas equation, right? So I know that my V1 is going to be equal to, so I know that PV is equal to RT, right? So P1 V1 is equal to RT1, right? So I'm just going to write 1, 1, 1, right? So if I'm looking for my V1, that's just going to be equal to RT1 over P. Over P1, right? And the reason I'm finding this, I always find that V always comes in handy. So I'm just going ahead and solving for it. So R is 0.287 for air, right? Let me just go ahead and write this all out. T1 is 800 and P1 is 1300. So our V1 should end up being and this is specific volume, remember, 0.17662 meters cubed per kilogram. Let me just double check myself. Yes. So we've gotten our V1, right? And what do we know about, we're looking for the mass flow rate, right? And we know that the formula for mass flow rate is rho time, which is our density, times V, which is our velocity, times the area, right? So this is sort of why we need that velocity, right? So our V1 is equal to 40 meters per second, right? And our A1 is 0.2 meters cubed, right? Meters squared. And what do we know? Okay, let me go ahead and write that. I might have to erase this work later on because we don't have too much space. I apologize. But basically, the relationship between density and specific volume, density is equal to 1 over specific volume. Okay, and that sort of makes sense, right? Specific volume is given in meters per kilogram, meters cubed per kilogram, right? Density is given in kilograms per meters cubed. So it sort of switches, right? So I know that my density, my density of the first part at the entrance, right, is equal to 1 over this number. And that gives me, I'm going to have to go ahead and erase this. That gives me that rho 1 is equal to 5.66202 kilograms per meters cubed, right? And that makes sense, right? So what we're gonna go ahead and get, right? Since we've calculated all of this, we now have the necessary tools to solve for our m dot, right? So our m dot is gonna be equal to, and remember we're dealing with a steady state, so we don't have to calculate m dot at the entrance and then m dot at the exit, right? So our m dot is gonna be rho 1 V 1 A1, and that should give us our m dot. So I'm gonna go ahead and calculate that, and we end up getting, it's gonna be 5.66202 times, and you have to remember that this V is velocity. You have to be very careful, okay? It's not specific volume. So that's gonna be times, okay, let me just write it out. It's gonna be 5.66202 times 40 times the area is 0.2, right? And that's gonna go ahead and give us our answer. And that should be 45.29616, and that should be kilograms per second, I believe. Let me just double check myself. Yes, and that's, we should get a number around there for the mass flow rate, right? So boom, we're done with our first. We're done with the first part of this question, right? That's our answer for the first part, right? The second part is now asking us for the power produced by the turbine. Now we're dealing with an open system here, right? What we get with an open system, we know we have our Newton's first law for open systems, right? Now Newton's first law for an open system is just, let me try and get a marker. I dropped my marker. Okay, so I can write out the equation. So we know that we have Q dot in, wow, okay, I'm just gonna write it in blue. Q dot in plus W dot in plus M dot H. I'm just gonna write 1 for in plus KE1 plus PE1. And that's all equal to Q dot out plus W dot out plus M dot H2 plus KE2 plus PE2, right? But we know a few things about turbines, right? We know that it's adiabatic, so boom, no Q, right? We can go ahead and cancel that out. We don't have to worry about that Q. We know that there is no kinetic energy involved or potential energy involved, so boom, we can cancel those out. And what we end up getting left with is something that looks like this. Sorry, there's no work in also for a turbine, right? Because turbines produce work rather than taking work in. They produce work at the expense of pressure, right? So we end up being left with something that looks like this. M dot H1 is equal to W dot out plus M dot H2, right? And it's very simple to solve from here. What they're asking us for is the power produced, right? So that's work out, right? Well, W dot out, which is power. So W dot out is equal to M dot H1 minus H2. And I can go ahead and combine, because this is the same M dot. So when I move that over, it's just distributive property, right? Then I'm left with H1 minus H2, right? And what I end up getting with that, I can go ahead and say this. Remember something when we're dealing with an ideal gas. H1 and H2, right? Delta H is simply given by Cp delta T. So M dot times Cp, are they asking for, yes, they're asking for capital work. So Cp delta T, right? That's going to end up being M dot Cp T1 minus T2. And right there, we're good, right? So we know that our M dot is, shoot, I erased it. It was about 45.2, let's say 45.29, right? That should be our M dot, around there. 45.3, okay, I actually have it on my calculator. Let's say 45.30, right? So I'm gonna go ahead and multiply that 45.30 times Cp for air is, they should give it to you on a little formula sheet, but I believe Cp for air is 1.005. Yes. So it's 1.005, right? Then we have T1 minus T2. And our T1, as we know, this is why it's good to write down all of your properties and everything, so I don't have to keep looking back at my paper and everything. But we don't have enough space, so I apologize for that. But T1 they gave to us was, I believe, 800 Kelvin. Yes. And then T2 was 400 Kelvin. So we end up getting this for our workout. And remember that if they were asking for small workout, like specific power out, right, W dot, right, since I keep saying work and power interchangeably, but know that W dot is equal to power and W is equal to work, right? But if they ask for like specific power, then you would just select, which is like little W dot, you just divide through by M, and we'd just be left with this Cp delta T, okay? But they asked for the big power out. So 45.3 times 1.005 times the difference of the two, which is just 800 minus 400, gives us this. Oops. 18,210.6. And that should be in kilojoules per second. So kilowatts. Because that W dot is kilograms, right? Okay, not to go too much into that, but just know it's kilowatts, okay? You can cancel, you can test out the units and everything, just know that it's kilowatts. I'm very confident of that. But so this is our second answer. You should get something around this answer, right? Now once we're done with this, what I like to do, right, is come back and now draw my second state diagram, or my state graph, my property graph, right? Because a lot of the time, along with accompanied by this sketch, they're gonna want you to draw a property diagram, right? So maybe like a PV diagram or something. And we know that with a PV diagram, right, this is why it was useful for us to calculate the air, I mean the specific volume, right? What we know, right, is that with, okay, let's say that this is, first of all, we know that our P1 was equal to 1300 kilopascals, right? Our T1 is equal to, or let me see, our V1 was equal to 5.66, I'm gonna say. Right, our P2 was equal to 100 kilopascals. And we never calculated our V2, so let's go ahead and calculate that right now. Now I know that my P2 is 100 kilopascals, my T2 is 127 degrees Celsius, which is 400 Kelvin. And what else do we need? R, right? We know that that's a constant for air, right? So my V2 is going to be equal to RT2 over P2. And you can go ahead and double check me on that. And this should be specific volume, right? If you switch around the ideal gas equation, it's going to give you that, okay? So our R once again is 0.287. T2 this time is 400, and that's all over, I believe, 100 kilopascals. 100 kilopascals. Now what we end up getting is that our V2 is equal to 1.148. Let me just double check myself. Yes. That's equal to 1.148, and that's meters cubed per kilogram, right? And what we end up getting, right, let me just write this here. What we end up getting, so we can make some observations, right? We know that our pressure dropped, right? And we know that our volume also dropped. Wow, that's weird. Oh, this is actually density. Our volume, right, is actually 1 over this, right? And that's why if I had a bigger board, we would be able to keep track of all of this. But that's why it's really important to write your properties, right, and keep them there. I mean, they're gonna ask you for your properties at the end of everything, so that's why you're always gonna have your properties there. But because I erased it, I sort of got it confused. But so we know that our specific volume is equal to 1 over that, right? And our specific volume is somewhere around 0.17668 meters cubed, and this is kilograms per meters cubed rather than the other way around, because this is density, right? And then this is switched, right? I hope I didn't lose you. This is our specific volume, right? This is our specific volume for state 2. So what we can see is that our pressure dropped while our volume went up, right? So we know that this isn't a phase changing substance, right? So we don't have to draw our little dome, right? What instead we draw, right? I'm gonna call this state 1. We saw that the pressure dropped, meaning that it's gonna go down, right? And the volume increased. So we're gonna get a graph that looks something sort of like this. And that's really it. Actually, this is state 2. And that's your PV diagram, right? Because it's an ideal gas, that's what our PV diagram ends up looking like. Yeah. So those should be what your sketches look like. Something like that. If you want, you can circle 1, circle 2, and they should give you credit for that, right? So I'm going to go ahead and erase these sketches just to give us a little bit more space. We're not quite done yet, right? These problems, these are generally the chunk of your exam that takes the longest, right? At least based on the type of exams that they give us. So what we're going to ask for is conditions, right? So conditions really, from what I've come to see, conditions, it's sort of like what we're dealing with in that state. So remember I said that we have air, right? So a condition would be ideal gas, right? That's what we're dealing with. Ideal gas. Really, I always come back to these at the end because I just start tacking on things, right? Some things might be more factual than conditions, but they're not going to dock you points for that most of the time because you still know what you're talking about. Conditions are just basically the state that we're dealing with, what we're dealing with in that problem, right? So we can say ideal gas. If you want to be fancy, you can say no interaction of air particles. Same thing. That's an ideal gas, right? What else? You can say adiabatic, I guess. Adiabatic. No Ke or Pe. Or negligible change in Ke and Pe. Or let's just say no. No delta Ke, delta Pe. Work produced by turbine, or no work in the turbine. So these are just sort of assumptions that we make, right? We because they didn't tell us that there was any work in the turbine, right? So I'm just gonna go ahead and say no work into turbine. And it's just moving along those lines, okay? That's basically what it is. There's no work put into the turbine, as we know. They're also going to ask you for physical laws, right? So the laws that we made use of as we did this problem. Now you can actually write out the actual laws for this, or you can write out the names of these laws. So you can say, first law for open system. We also use the ideal gas law. We also used 1 over specific volume is equal to density. What else do we make use of? I mean, that's really it. What else? Yeah, that's what I've written down. So that's really it. That's really all you need to solve these types of problems. I'm sorry I don't have a bigger board so that I can keep everything on the board at the same time. I'll try and work on that, but this is really all you need to solve these types of thermal problems. It's pretty simple once you deal with it. If you didn't understand anything that I did, please feel free to leave comments in the comment section. Please tell your friends. Don't forget to like and subscribe, and let's keep learning thermo. Thank you.